This is Algebra 2 with trig, 6.5, day 1. This is graphing square roots and cube roots. Okay, in 6.4 we saw that the graph of y equals the square root, and we looked at the graph of y equals the cube root. Okay, these are examples of radical functions. Now we'll be graphing them in the form of y equals a, the square root of x minus h plus k, and also a, the cubed root of x minus h plus k. When we look at these graphs, we have a parent function, which is for the square root graph, it's just a square root of x. It has a specific form. To figure out where the dots land, we could make a table. And we would use numbers like maybe -1 and 0, 1, 4, 9. Those would be some common x values to use. When you plug in -1 into the square root, we get an imaginary answer. You can't take the square root of a negative. There's no two numbers, or the same number, that multiplies itself that makes -1. The square root of 0 is 0, square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3. So we can graph out and connect our dots. So you can make a table to graph your parent function. Y equals the cube root of x. The cube root of x is a little bit different. It looks a little bit like the a square root, but it goes in both directions. The reason why this is true is because we look at numbers like -8, -1, 0, 1, and 8. If you're looking for three numbers, because this is the cubed root, three numbers that multiply to be -8, and that would be -2 times -2 times -2. That makes -8. So that's why the graph exists over here when x's are negative. The cubed root of 1 is 1, and the cubed root of 8 is 2. So if you need to plot out a table so you can figure out where the graph goes, you can do that for a parent function. So we're going to use the RST format for these. So that means we have to graph the parent function, we have to graph a reflection if possible, a stretch or shrink, and then a translation. All the translations will be in a different lesson. So we're going to start out with the parent function, which is y equals the square root of x. We've talked about how those values 0, 0, 1, 1, 4, 2, 9 and 3, 16 and 4, and so forth. The only ones that are going to fit on our graph go up to x is 4. So we graph that out. And it's y equals the square root of x. That's our parent function. That's where we're starting from. Next we might look at a possible reflection. But we notice that a is greater than 0. So there's no reflection. Next, we're recognizing that the absolute value of a is less than 1, so that we're going to have a shrink. That means that the graph is going to come towards the x-axis. What we're going to do is take every y value from our table and multiply it by the absolute value of a, which is 1/4. So we're going to take 1/4 and times it to the y value of our first point. And that gives us 0, 0. we multiply 1/4 to the y value of each of the points. One-fourth of 2 gives us a half. So these are our new coordinates that we would be using. Another way we could do that is to come over here to the graph. We know that this is going to shrink by 1/4, so instead of going up a full 1, we're going to go to a fourth. Instead of going up 2, we know we got to break that into 4 equal pieces and do 1/4 up to a half. So this is y equals 1/4 the square root of x. And that is our final graph for this equation. Look at the domain. The domain are the x values that you could be used, perhaps to be, the domain are the x values that are being used for the graph. That is, x is greater than or equal to 0. The range are the y values that are being represented through the graph. The farther the x went out, the higher up the y would become. We look at this equation, and it's y equals -2 square root x. So it's a square root function. So I'm going to start with the parent function, 0, 0, 1, 1, 4, 2. I'm going to look at if it has a reflection, and because the a value is less than 0, I'm going to multiply all of the points by a negative. We'll call it a -1, but it's just multiplying the y values by a negative. So we take the y value of the coordinate 1, 1, we multiply it by a negative, and we're going to be at 1, -1. We get 4, -2, just by multiplying by the reflection, by the negative. That flips it over the x-axis. So if we looked at what this would do to our graph, you could start out with your parent function, so here we have y equals the square root of x. And the reflection flips it over the x-axis. If you would prefer just to use it on the graph, you don't have to make the tables along here. So that's the reflection of the square root of x. Next, we're going to notice that the absolute value, we're not considering the negative aspect of it. The absolute value of our a, which is -2, is greater than 1. So this is a stretch. That's not overly important. If it's a stretch or a shrink, it just gives us an idea of what to expect. But I'm going to take my current point, and I'm going to multiply the y values again by the absolute value of a, which is 2. Again, I land at 0, 0. One comma -2. 4 comma -4. So if you like making out the table so you can see each step, notice I'm not taking points and plugging them into an equation. I'm actually using the Algebra 2 facts of a reflection and a stretch and later on a translation to help develop what these coordinates would be. I'm also a fan of just using the graph itself Now since we've reflected it, we know that we have to come down twice as far because the a value is 2. So we're going to multiply that negative 1 by 2 and come down to negative 2, come down to negative 4, come down to negative 6. So here it would be y equals negative 2 square root x. Now we're looking at the cubed root graph on the second page. Well, a cubed root graph, the parent function is just the cubed root of x. That has negative 8, negative 1, 0, 1, and 8. So we get negative 2, negative 1, 0, 1, and 2. We can come over to our table, to our graph, and graph that out. So we have y equals the cubed root of x. Want to be sure to label your graph. So we notice with the reflection that we're going to take every one of these y values and we're going to multiply it by a negative. So that changes it to become a positive. If you prefer not showing all the other steps of plugging in the negative, like I have here, then that's fine. If you want to show those, that'll work also. If you just want to come over to your graph and you know that the negative reflects it over, you're welcome to use that process also. So that's y equals negative cubed root of x. So now we know that the absolute value of a is greater than 1, so we know that this is going to be a stretch. So that means I'm going to multiply all of my y values by the absolute value of a, which happens to be 2 again. So I find my new coordinates. Another way to do that is to look at your graph. Instead of coming down 1, you're going to come down twice as far, down to negative 4, up to 1, up to positive 4. And we're getting y equals negative 2, the cubed root of x. We know that the domain for this, notice that you can use positive or negatives in your table. So it's going to be all real numbers. In the range, you get positives, you get negatives, it goes up forever, it goes down forever. You get all real numbers. That reminds me, probably on the other side, I don't think we ever did our domain and range. Let's look at that real quick. It looks like our final graph, we used x values that were greater than or equal to 0, and our range was below the x-axis. So that was less than or equal to 0. Here we have y equals a half cube root of x. So we're going to start out with the parent function. There's going to be no reflection. but we know that a is less, the absolute value of a is less than 1. So we would call this a shrink. So we're going to multiply all of our y values by a half. When we do that, we can graph our parent function. So we have our parent function, which is y equals the cube root of x. This one did not have a reflection, so there's no reflecting it over the x-axis, but we do shrink it by a half. So instead of going up 2, we're going to go up 1 to a half. This is going to have a very small adjustment as it shoots across the graph. So here we get y equals half cubed root of x. The domain, what are the x values that you could possibly plug in? They're all real numbers. And the range, you're going to get all possible answers. Biologists have found that the shoulder height in centimeters of an elephant can be modeled by this crazy equation, where t is the elephant's age in years. So we're going to take this equation. We're not going to actually graph it by hand. We can use a graphing calculator and then sketch that onto our graph. So using our calculator, we would go to y equals, type in 62.5, then there's a math button, and go down to the cubed root. We're going to use, they're suggesting to use t, but on your calculator it has a t, but that's not the same type of t. So we just put in x plus 75.8. And when we graph it, we get something that looks like that. Now, we're interested to see when is the height, 200. So we can look at our table. Second graph will give you a table. We're interested in when we would get about 200. Okay, 189, 195, there's about our 200 spot. So when x is 8, we're up near 200. So I'd go to Window, our x value of 10 seems okay, it's larger than what we need of 8. But the maximum value needs to be much more than 10. 200 is where we hope it to be, so let's go larger than that. And hit graph, and you'll see how it curves up and curves through. So we can come over here to ours. We can curve up and curve over. Now what we're looking for is a line to come through here called y equals 200. So we're going to go to y equals. Down in y2, type in 200 because we want to know where the 200 intersects this graph. So right over here. To find that exact location, we can hit second trace, which is the calc, down to intersection. Now it's asking you some questions. It says first curve. What that means is your first equation. Is this one of the equations you're working with? And the answer is yes, so we hit enter. Is this the other equation that we're working with? We only have two equations. Of course it is. Hit enter. It asks you to guess. That means it wants you to help identify about where's the answer. If there's more than one, it needs to know which one you're talking about. Well, in this graph, there's only one. So we can hit enter, and it's happening out here at 7.84. So 7.85 if you're rounding up to the nearest hundredth. So to figure out when y is 200, our calculator gives it to us at 7.85. So we know that the years is approximately 8. An elephant will be 200 centimeters at approximately 8 years old.